I've grown fascinated with marine navigation over my time as a professional and recreational mariner. Of course, there's lots of ways to navigate now. Most common is satellite navigation, or GPS. It's a constellation of satellites in space that send precise time signals down to Earth. Using circles based on those time signals, we can find our position that way. Likewise, there's radio navigation, such as LORAN or radio time signals. These are radio signals put out from a known position and correlated on an electronic device to help you find your position at sea. There's also radar navigation. Radar navigation, or radio detection and ranging, sends out radio signals from a transmitter on your ship, and it listens for echoes. Using the speed of light and transmission of that signal, it can calculate the distance to an object out at sea. In my Pacific sailing days, I also learned about traditional wayfinding techniques, such as using waves, clouds, the sky, the smell, animal signs to find signs of land. Similarly, there are traditions of using guide stars and celestial navigation for wayfinding techniques in the Pacific Island region. While teaching as part of an environmental science program, I learned from maritime historians about traditions of European and Arabic navigation, including sextants and quadrants and staffs and techniques such as that. So let me turn over the watch, we'll head below and we'll talk a little bit more. In this film series, we're going to focus on the late European style of celestial navigation, the St. Hilaire altitude intercept method, as practiced by commercial mariners and recreational yacht sailors today. Let's take a look at some fundamentals of navigation, and then we'll dive into the marine sextant. There are many ways to navigate a vessel, but in the vein of eventually trying to understand celestial navigation, it's helpful to review several different types of navigation that are out there. The first and most simple is going to be what's known as piloting. This is where you're out there on your boat, maybe floating along, and you notice some land features that are out there, and you can match them up to land features that are on a chart and determine roughly where you are based on that chart. That chart could be like a verbal or an oral history from your people. It could be a paper chart, an electronic chart, but using natural features and matching them to a known template is piloting. Next on our list might be something called wayfinding. Early Polynesian navigators, for instance in the Pacific, would use clues such as cloud formations or the presence of birds and drifting debris in the water, or the changing patterns of swells to indicate that they think there might be some land out there hidden behind the horizon. So this wayfinding technique uses changing colors, natural clues, coupled with an oral tradition of where something's supposed to be, can help you navigate pretty amazing journeys from island to island. For example, all stars have a known pattern of rising, setting, transiting throughout the night. And if you can memorize this information through oral tradition or creating a chart or a stick chart as they do in the Pacific, you can help orient yourself to other landmarks at sea. For instance, some stars pass directly overhead of islands at some point during the night. And so if you are on that same path, you're going to notice that star passing overhead of you, and you're kind of on your way to that island. It indicates the latitude of your destination. Next up on the types of navigation that are out there is dead reckoning, which is sometimes known as DR, or deduced reckoning. And this allows you to use the places that you've been, the speeds that you've traveled, the directions that you've been heading to predict where you're going to be in the future. This is a good way to estimate where you're going to be. However, it is subject to things that are out of your control, like wind and current, kind of setting you off track. So understanding where you were, keeping careful track of it, will help you predict where you're going to be. Dead reckoning. Celestial navigation is used when you're out on the open ocean and there's no other landmarks except maybe the sun or the moon, the stars, and the planets that are out there to help you guide your way at sea. Knowing where these bodies are, or more specifically where they're directly above on Earth, will allow you to figure out how far you are away from that spot. Celestial navigation is best used out on the open ocean. It kind of grew out of wayfinding and dead reckoning techniques to provide a greater sense of accuracy. But you need good tools in order to measure these type of things. So hence the development of the sextant and the backstaff and various tools and tables to help encompass all this information in the mariner's ship. There's a few types of electronic navigation as well. Radar navigation, for instance, bounces a signal off objects, and using the relationship between speed, distance, and time allows you to figure out how far you are away from a known object to help you plot those on a chart. Likewise, in the modern age, satellite navigation allows you to figure out your position very precisely. It uses time signals to create these circles of equal time, and where they cross is going to be your location. Generally, you need 3 or more of these time signals to get your two-dimensional position on Earth, and you would need a fourth one if you were like climbing a mountain or something. But the more signals, the better. This is actually very helpful when you're thinking about celestial navigation as well. These circles of equal time are kind of analogous in celestial navigation to circles of equal altitude, which we'll use for our celestial bodies. There's also an electronic technique known as LORAN, or long-range radio navigation. It relies on a known position which puts out parabolic radio signals in all directions. And if you combine a couple of these signals, you can determine your fix. LORAN was a great technique in the 1970s and 80s. It has since gone out of style, but it's a valid technique of using known positions in radio broadcast signals to help you determine your position. There's also simple things such as radio direction finders, where an island out there might have an antenna broadcasting, and it helps you pinpoint the direction to that island. Being a good navigator relies on using the right tool for the job. So if you're departing from a harbor and you're heading to another place across the ocean, you're going to use piloting techniques in these vicinities. You might use radar for electronic navigation. You might use GPS navigation, of course. When you're out in the open ocean, that's when celestial navigation really comes into its own and allows you to use the lighthouses in the sky as opposed to kind of the lighthouses on islands. As you get closer to your destination, you can shift back to piloting techniques. The good navigator realizes that in this course, we're studying just one element of navigation. You should become proficient in all the other types, electronic, terrestrial, piloting, etc., to become a better and well-rounded navigator. So this is a great time to just give the broadest possible overview of what we're hoping to accomplish with this course and how it's organized. For me, I think there are 5 big steps to any celestial navigation sighting, whether it's the sun, the moon, the planets, or the stars. The first thing we're going to do is observe the object with a sextant, and we're going to correct it for a few key things to make that measurement extremely accurate. And that's the first part of the course, kind of the first section, observing and correcting the object. That observation is something that we're going to keep in mind for later in the process. The second step, once we've kind of observed the object, is to find that object in an exact position over the Earth at any particular exact time. So for example, the sun right now is directly over some point on Earth. If they looked up, it would be directly overhead. It would probably be really hot, and there would be like no shadows. Same goes for any celestial object. There's a book called the Nautical Almanac will help us find this celestial object to the nearest second to any latitude and longitude. We'll introduce some terms, there'll be some nuances, of course, but we want to be able to find that object. Once we've done that, the third step in the process is to build a navigational triangle. If you remember back from your middle school days, if you can learn sides and angles of a triangle, you can calculate all the rest. And so we're going to very strategically build a triangle using certain data from the previous steps to allow us to use another book in step number 4 to solve that triangle. That book just kind of calculates sides and angles and spits something back out. So if we know what to ask, we can get good data back. Once we've solved that navigational triangle using the tools available to us, we're going to compare the calculation to the observation and find the difference and then plot that on a real chart, a human scale chart. Otherwise, we're dealing with the whole Earth. Things are really, really far away when we're talking about these celestial objects. So we want to be able to plot this on a real size chart. This whole process is known as the St. Hilaire method or the altitude intercept method. It's going to be how the course is organized. Each chapter, each part is focusing on key skills from that element. And then at the very end, we'll put it all together and we'll solve these celestial sights for the sun, the moon, the stars, and the planets, and unlock that celestial navigation ability for you. So let's take a look at the marine sextant. We'll go out on deck and take a look at some of the fundamentals of this kind of magic device that we use for celestial navigation. The main tool used for celestial navigation is the marine sextant. In addition to tables and a timepiece, this is going to be your go-to device. Historical tools include things like the backstaff and the kamal and other methods. They're all very interesting for historical purposes. We're going to focus on kind of the modern marine sextant in this course. The general principle of operation is that light enters one mirror, bounces off another, and then enters a telescope for you to look through. The main parts to the sextant include the handle. For right-handed people, it's very convenient. For left-handed people, not so much. The index mirror is the mirror up here where the light first arrives. So you can kind of see that mirror there. The index shades are sunglasses for the index mirror. So don't ever look at the sun directly. You're going to burn your eyeballs out. The horizon mirror is the one that doesn't move, right? So it doesn't move, and you're going to look through the telescope at the horizon kind of out there. And this one is split. So some sextants are different. This one is split, so between a mirrored surface and a clear surface. There's also horizon shades for those as well. And there's a telescope for you to look through that's sometimes adjustable for you to kind of make adjustments and focus on there. This is the index arm right here. This is the part that moves, and there's two ways to move it. There's the micrometer drum, which moves it very slowly, and the index release, which moves it very quickly. This down here is the arc, where you measure the degrees, and this right here is kind of the vernier scale, where you measure the minutes. This tool is your life. Generally, the sextant is going to take care of itself. So if you wash it with fresh water, if it gets salty, if you keep a small silica pouch inside of the box, and if you use lens paper on the mirrors instead of just like a random rag, it's going to go a long way to making the sextant last a long time. You can also use some little oil on these teeth. Usually sextants, when you buy them, come with a little bit of oil, or you can just use a little bit of kind of whatever lubricant you have to make sure these teeth are moving cleanly. The sextant, though, like all human objects, does have occasional error. Some that are kind of built into the sextant and some that you can control. Here are the sources of error and the means of correcting it. There's three sources of error that are really not adjustable. They might include things like prismatic error, where the shade and the mirror, or the horizon mirror particularly, are misaligned, and therefore we've got a little bit of a gap where sunlight can come through. Prismatic error. You've also got graduation error, in which the metal parts of the sextant are not necessarily manufactured to the right degree of accuracy, or the metal heats at different rates. There's also centering error, where the index arm, when it's manufactured, is not actually manufactured to the correct tolerances to center it up. A lot of times for these errors, which are not really, correctable by you, the instrument manufacturer might send you a card that says what the index or the instrument error is for a particular sextant. So you can use that for your calculations. There's a couple of corrections that are adjustable by you. So the first is perpendicularity, and that occurs when the index mirror, this one right here, is not perpendicular to the frame of the sextant. You can adjust it with this screw, depending on your manufacturer, but this screw is generally the one that's going to fix the index mirror. You can measure this with a technique using similarly sized objects placed on the frame and observed through the mirrors. If you see that they are aligned, you're good to go. If they're offset, you can adjust that screw to bring them back into alignment. Side error occurs when the horizon mirror is not perpendicular to the frame. So if the mirror is not perpendicular to the frame, you've got some error. Well, you can adjust it with this screw right here. This can be measured using a known object and tilting the sextant back and forth so that you can see if everything is perpendicular. Index error occurs when the horizon mirror, again, is not parallel to the index mirror. You can adjust it with this screw right here. This is a common error. It should be determined every time the sextant is used, and usually it's mathematically removed from your calculation unless the index error is exceptionally large. I like to think greater than about 5 minutes of arc, somewhere in the 3 to 5 minutes of arc. If it's less than that, you can just remove it mathematically. Collimation error occurs when the telescope on the sextant is not necessarily aligned correctly, or if it wiggles around a little bit. So you can correct this by just putting it back in its place and tightening the screw down to make sure that it is aligned. Beyond that, it would need to go to a manufacturer to repair it. So if you treat your sextant right, it's going to take care of you. The first thing you'll do when you're trying to take an observation of a celestial object is to observe the index error, which was described earlier and can be mathematically removed from any site that you take. Always be careful to use the appropriate shades so that you don't burn your eyeballs out. When it comes to taking a site, the general process is to observe the object through the telescope with the sextant set to 0 degrees. Then, keeping the object in view, you slowly lower the angle of the sextant until it is parallel to the horizon, while simultaneously moving the index arm forward, either using the index release or the micrometer drum. When the object is close to the horizon, you will swing the sextant back and forth so that the object traces an arc around the horizon. You'll be adjusting the sextant continuously until the object just touches the horizon at its lowest point. Then you'll note the exact time and the sextant reading. Reading a sextant can be very tricky, but it's helpful to remember to think of it in two parts: the degrees and the minutes. The degree measurement is off the index arc. Whenever the whole number of degrees has been surpassed by the index arm, that's your value. It's very easy to make an error of like 1 or 5 or 10 when you're reading the sextant, so be very careful. So for example, right here, we are just a little bit over 55 whole degrees. So here's 50, 51, 2, 3, 4, and 5 degrees. And you can see we're just a little bit past it. If I continue to move past it, now we're a little past 56, a little past 57. And as you get closer and closer to 60, you can see it's tricky to say, hey, am I on one side of 60 or the other? Right? So reading the whole number of degrees from the index arc is the first step. The second step is reading off the vernier scale here on the micrometer drum. So this is the drum over here that spins, and this is the reading scale over there. So note the decimal 0 point right there, and it's lined up with the 0 on the left side on the micrometer drum. So this reading right here would be a total of 60 whole degrees and 0.0 minutes. If I went up, say, 2 minutes, this would be 60 whole degrees and 2.0 minutes, because the 0 is lining up with the 2 on the minutes arc. You can get very detailed. You can get up to tenths of a minute with this type of sextant, and every sextant's a little bit different, but this is the idea. For now, though, I really recommend you focus on getting degrees and minutes down. So let's do another example here. Right now, we've got 61 degrees and 5.0 minutes over here. So 61 degrees, 5.0 minutes. If we cranked it up, you can see that it's now 61 whole degrees and 30 minutes of arc there. When we do get into the vernier scale on these tenths, the way that you're going to work it on this particular sextant is, let's say we end up right about there. We would have 61 whole degrees, and then we look at what has been surpassed on the left side. So there's 30, 31, 32, and we're a little between 32 and 33. So it's tricky to see where that 0 lines up, but it's somewhere between 32 and 33. So to get the tenths on this sextant, we look at which line on the right side best lines up with something on the left side. So it's not 0.8, it's not 0.6, it looks like it's 0.4, lines up perfectly with something else, right? So it's not 0.8 because that does not align. It's not 0.6. It looks like it's 0.4 is the correct solution. So 61 whole degrees, 32 minutes, and decimal 4 of a minute would be our final answer. Don't get discouraged with this trickiness right here. We're talking a couple of 100 yards of accuracy. Focus on the degrees and the minutes on your particular sextant, and you're going to do great. So although the majority of time spent on any celestial site involves the reduction process, getting this part down solidly is going to help your skills as a sextant operator and avoid the disappointment of a bad site later on. An alternative method of observation involves turning the sextant upside down and bringing the horizon up to the object. This is helpful when the object is faint or in partly cloudy skies. Once you have the object and horizon close to each other, you can turn the sextant back into its normal configuration, sweep the horizon until the object is visible, and continue the sight. Previously, we've discussed some of the errors that can strike at a sextant, but the most common error you will routinely deal with is index error. Index error happens when the two mirrors are not exactly parallel. However, it's usually easier to mathematically remove this from the sight rather than to try and adjust the mirrors on the sextant in real time. You should check the index error every time you take a sight. The key concept to remember is that index error can either be on the arc or off the arc, meaning that if the index error is a little above 0, you need to subtract it. If it's a little below 0, you need to add something back on to mathematically correct it. To measure for index error, you're going to set the sextant to 0 and observe the horizon. The horizon should appear like a straight line on both sides of your sextant. However, sometimes it's common for there to be a little bit of a step in the horizon, where one side is a little bit above the other. If one part of the horizon is stepped or broken above or below the other, you're simply going to adjust the sextant until they're back in alignment. Then you'll read the sextant and pay close attention to the direction of the minutes of arc that you notice if the horizon is in fact stepped. In the first situation, you perform the procedure and the sextant might read something like this. You would read that as 2.0, but in reality, you need to use this 0 as kind of an anchoring point. And in this case, you are 2 minutes on the arc, in addition to the arc. So in this case, mathematically, we would need to subtract 2.0 to get back to 0. In the second situation, after you've checked for index error, maybe the sextant reads something like this. You would read that as 58.0, but that's not the value we're looking for. Again, remember, this is kind of the anchor point, the 0. So you're 2.0 in that direction from the 0 point. So in this case, your index error is 2.0 off the arc. And so you need to add it back on to get back to 0. So the takeaway from this is if you are a little bit above 0, once you've measured the step in the horizon, you need to subtract that value to get back to 0. And if you're a little bit below 0, you don't take the actual number, rather the number of minutes below 0, and you would add that back on to correct back to 0. So if it's on the arc, you have to take it off. If it's off the arc, you need to add it back on. Let's take a look at an example problem regarding index correction. In this example problem, you observe an object at a height of 40 degrees and 05.0 minutes. So you've measured this and read the sextant, and there's your value. This is what's known as the HS, or height per sextant, or height of sextant. It's the initial reading of a celestial body. You previously determined that the index error was 2.0 minutes on the arc for index error. So since we know that the index error is on the arc, we always need to subtract it to get our final answer. And if we do that, we get 40 degrees 03.0 minutes. This is what's known as the HA, or height apparent. This height apparent is the height of an object corrected for index error and something else that we'll learn about later. So take a look at the example problems provided and see if you can master the ability to apply index correction. The Nautical Almanac is a key document for you in your study of celestial navigation, and learning its intricacies is important. One of your tasks in celestial navigation is applying standard corrections, and the Nautical Almanac is the place that you're going to go to find those. These standard corrections include things like index correction, which we learned about previously, as well as height of eye correction, altitude corrections, and non-standard condition corrections, all of which we'll learn about in subsequent lessons. For now, let's take a look at the front part of the Nautical Almanac and learn a little bit about some of the key features. First thing to note, it's the 1981 Nautical Almanac. It's the standard training book and we'll use for this course and all other celestial navigation exams that you'll take in the United States. It's also a joint publication from the United States and the United Kingdom. So these two organizations work together to have the same content for both of our countries. The table of contents is kind of unremarkable. There's nothing really of note in here, but the front of the almanac includes a few important things. One is going to be altitude correction tables, which we'll get into in a little bit. So always be able to find these altitude correction tables, as well as corrections for non-standard conditions of temperature and pressure. Moving on, in the Nautical Almanac, there are holidays, days of the week, eclipses of the moon. There are diagrams for eclipses. There are planetary diagrams to be able to identify which planet is up in the sky. The middle section of the Nautical Almanac includes daily information about where the sun, the moon, the planets, and the stars might be. And then towards the back of the Nautical Almanac, there's a few key features in there as well. First, there are instructions on how to do mathematical sights of celestial objects. Then there are some star charts, and there are corrections for converting arc into time, so degrees into minutes of time, as well as all the increments and corrections you might need to do any of your celestial navigation calculations. At the very back of the book, this is important, there are altitude correction tables for the moon, which we'll learn about as well. So for the next several topics, we'll focus on how to make standard corrections to the sextant using the Nautical Almanac's tables for height of eye, altitude, dip, and non-standard conditions. Despite appearances to the contrary, when you make a sextant observation on a boat, you are not actually at sea level. Your eye is above sea level by your height plus the distance from the deck to the sea. Although it is a small amount, it is important. All almanac figures are derived based on an observer at sea level. In terms of geometry, we're talking about kind of a little bit of an esoteric definition here, but there is a difference between the visible horizon, which you can see, and the sensible horizon in terms of the definitions of planetary geometry. When you observe through the sextant is almost always too great, and therefore you need a negative correction in almost all cases for your height above the surface of the ocean. Just of note, if you are using an artificial horizon to practice celestial navigation sites, this correction does not apply. The correction we're looking for is found in the front part of the Nautical Almanac, and it's in a table called dip, which is going to correct us for our height of eye. So if we look at this table carefully over here on the right, it says dip, it says height of eye, correction, height of eye, correction. So we've got feet here and meters here. We've also got small amounts of meters here and small amounts of feet here. So I'll just zoom in a little bit so we can take a closer look at this. So as an example, if your height of eye was 3.0 meters, your correction is going to fall in this vicinity. Typically, however, our value is going to fall between one of these values. So let's say we were measuring in feet and our height of eye was 9.6 feet. Well, here's 9.2, and here's 9.8, so our correction is negative 3.0. You're going to choose the correction between the values that bracket it. As another example, if our height of eye was 1.5 meters, well, we're over here in the small category, and the correction is going to be negative 2.2. And lastly, if our height of eye was, say, 3.5 meters, we'll use the meters column. 3.5 is not listed, but 3.4 and 3.6 are, so our correction is negative 3.3. Let's take a look at an example problem involving height of eye corrections using the dip tables. So if we observed a celestial body at a height of 40 degrees and 05.0 minutes, that's our height per sextant, or height of sextant. There's no index error in this case, so there's no correction for index error. However, we did note that our height of eye above the surface of the sea was 10 feet for height of eye. So what would be the height apparent in this case? Well, we're going to use the dip tables, and we'll see that if our height of eye is 10 feet, it looks like our correction is going to be negative 3.1 in this case. So our height of eye is 10 feet, and there's no 10-foot value, but there's 10.5 and 9.8, so we're going to interpolate or choose the value between those. So if our correction is negative 3.1, then our final answer is going to be 40 degrees 05.0 minus 3.1 minutes, or 40 degrees 01.9 minutes for our height apparent. So in summary, our height apparent is going to be the height of sextant corrected for index error and height of eye, or dip. Those two corrections contribute to the height apparent. Once we have corrected a sextant site for index error and dip, we've obtained the apparent altitude. The next step is to correct this figure for variables including the diameter of the object, the refraction of the atmosphere, the temperature, the pressure, the proximity to Earth, etc. Although it sounds complicated, it's generally pretty straightforward. It's wrapped up into like 2 corrections for normal conditions, and then a couple of extra ones if it's abnormal conditions. The first thing to consider is refraction. Refraction is the bending of light through the atmosphere. So let's imagine you're out there on your boat and there was an object directly overhead. Well, you're not looking through too much atmosphere, so there's not going to be a lot of bending. However, if the object is low on your horizon, you're looking through a lot of atmosphere, so there can be a lot of refraction and bending due to the differences in the properties of the air between the observer and the object. The next one to consider is semi-diameter. Semi-diameter is the term that we use to account for the fact that all celestial calculations are based on the exact center of a celestial body. However, some of them, like the sun and the moon, and even Venus and Mars, are a little bit bigger. And so we just observe the lower limb or the upper limb of the object and mathematically account for the semi-diameter to get back to the middle. Another thing to consider is that the sun's proximity to Earth or the moon's proximity to Earth change with the seasons, and this can affect our celestial navigation calculations. Making altitude corrections in normal conditions is relatively straightforward. We're just going to use these tables here. So there's tables for the sun based on the season, as well as the lower limb and the upper limb. There's tables for the stars and planets, specifically Venus and Mars, and sometimes Jupiter, but in the 1981 almanac, only these 2 planets have additional corrections. Likewise, at the back of the Nautical almanac, there is a table for altitude corrections of the moon with instructions, which is great. So take a look at these tables, and they'll become pretty apparent to you as far as what you're going to do. But in essence, for the sun, choose the season, choose the limb, choose your apparent altitude, and you'll see your correction is right there. For the stars and planets, simple as choosing your apparent altitude with a correction, and then adding an additional correction for Venus and Mars depending on the season. Let's take a look at an example problem involving normal conditions of temperature and pressure regarding altitude corrections. So in this problem, we've observed the sun's lower limb on October 11th, and that's going to be important as we move forward into this problem. We previously determined that the apparent altitude, and remember, this is the altitude corrected for index error and dip already, is going to equal 43 degrees, 13.0 minutes. What is the observed altitude? We're transitioning from HA to HO in this case. Well, in order to solve this, we need to look at the apparent altitude correction tables for normal conditions of the atmosphere. And so the first thing to note is what object did we use? It was the sun. Second, what month? It was in the October to March time frame. Third, which limb? Usually it's the lower limb, so we're going to be definitely in this column here. The way we solve this problem is we look in the apparent altitude table for our value, which is 4313. So you'll almost never see the exact value, but here's 4359 and here's 4108. So the correct answer is going to be somewhere in between them, and in this case it's plus 15.2 minutes. So if we add 15.2 minutes, we'll end up with our final answer of 43 degrees 28.2, and that is our HO, our height observed. And this is the ultimate goal of step 1 of our process of learning celestial navigation, is getting ourselves from the height of sextant to the height apparent and now to the height observed. The moon is a very challenging object to work with because it's very close to the Earth and it changes phases and it alters the visibility of the horizon when you're making sights. However, it is in the sky during the day half the month, which is a nice thing to do if you wanted to do a sun and moon daytime fix. These are the corrections in the back of the Nautical Almanac for the moon. So the moon has its own dip table. First of all, it is identical to the one in the front of the almanac. It's just kind of reproduced here for your convenience. The first correction is going to be in the upper part of the table. This accounts for the refraction and the semi-diameter of the moon, similar to the sun. The second correction is in the lower part of the table and accounts for what's known as horizontal parallax, the proximity of the moon to the Earth. It's important to note the table has values for each of the upper and the lower limbs. So you'll note that. All corrections for the moon are added to the apparent altitude, except 30 minutes is subtracted when you're using the upper limb. Luckily, there are instructions right here to help you remember that weird fact. The moon is challenging but enjoyable to observe, and it can result in excellent daytime fixes with the sun at the right time of the lunar cycle. What we're referring to when we talk about parallax is just the way that the rays from the object intersect with the Earth. So for instance, a star is super far away, and you can consider the rays of light coming from that sun way off in space to be parallel. So any observer on Earth is really going to observe basically the same thing. The moon, however, is much closer and it's quite large in the sky. So the rays from the moon are not parallel. And this non-parallelity is called horizontal parallax, and it just simply needs to be accounted for when you're using the moon as a celestial sight object. Let's take a look at an example problem regarding the moon. In this case, we've observed the lower limb of the moon. It's important to note which limb we observe. The apparent altitude, or HA, was 29 degrees and 10.0 minutes. The horizontal parallax was 54.0 minutes. This is something we'll learn to look up later in the course. What is the observed altitude? Well, in this case, we're going to need to use the altitude correction tables for the moon. So we'll take a look at the altitude correction tables for the moon, and we'll note the first correction is going to come from the upper left column here. So first thing we do is we look for the apparent altitude. Now it's a little different than the sun. In this case, it's broken out into degrees along the top and minutes along the side, and then a whole bunch of graduated amounts here in the middle. So we're looking for 29:10. So where's 29? Here's 29 and 10. So the corrected value here is 59.3 minutes. Just note that you can interpolate these values if yours is not exactly 10. Like if it was 11 or 12 or something, you can interpolate. Generally, the graduated ones are sufficient for accuracy. So 59.3 is going to be the first correction that we make. All corrections to the moon are added unless you're doing the upper limb. The second correction has to do with horizontal parallax. So in this case, the horizontal parallax was given to us as 54, and we used the lower limb. So here's 54 for horizontal parallax. Here's the lower limb, but we need to stay in the column that we used earlier. So earlier we were in this 29 column, so we need to stay in that column, look for the lower limb and the horizontal parallax of 54, and see that our correction is 0.7 minutes. Again, they're always added. So if we do this math up, we'll end up with our height observed, which is our total goal here, of 30 degrees and 10.0 minutes. So again, our goal is to get from HS to HA to HO as part of this process. The moon is a little bit more complicated than the other objects, but not sufficiently so that you should ignore it. So in this part of the course, we've really focused on HS to HO. So the height of the sextant to the height apparent to the height observed, taking into account index error, dip, atmospheric refraction, temperature and pressure, non-standard conditions, etc. will get us from a sextant height to an observed height. That observed height, we're going to pocket away for later, and eventually we're going to calculate and then compare to what we measured to determine our celestial line of position. So hopefully at this point you feel very comfortable with that process. That is step one of kind of 5 in the real big process of celestial navigation reductions. I would encourage you to practice the skills that you've worked on so far, and when you feel very confident in those, go ahead and move on to step 2 in the process, which is finding the geographic position of any body in the sky at any time.